Hello, my name is Laura Beester. I'm a PhD student at the University of Michigan, and today I'm going to be presenting our work on building location embeddings from physical trajectories and textual representations. First, I'm going to present a quick outline of our work. I'll start with an introduction, then talk about our data collection, our methods, our experiments, and finish with some conclusions. Now I'm going to give an overview of our work. Dense vector representations, or embeddings, are commonly used in NLP to represent words, and they have also been applied to locations. For example, I could create an embedding for my home. We use location trajectories and text data to create embeddings. And to evaluate those embeddings, we explore two different types of tasks. First, surface level tasks to better understand what location embeddings are encoding, and then downstream tasks to see if they can be used for predicting personal attributes. In the paper, we include more tasks in our evaluation than I'll discuss in this presentation, and so if you're interested, I encourage you to check that out. Now I'm going to talk about the research questions addressed in our work. First, do location embeddings encode meaningful semantic information? And by this I mean, do they encode information that humans would say defines a location? Next, what sources of data are most informative about locations? We use both location trajectories and text data, as I mentioned earlier, but we also look at multiple sources of text data like Twitter and Reddit. And then third, can location embeddings aid us in downstream tasks? And specifically, we look at human-centric prediction tasks. An example use case that I'd like to go over is health monitoring. One downstream task that we look at is depression detection. And a possible application is individual level monitoring for people who are already in treatment for depression and seeing a therapist. If they aren't able to see a therapist every week, this could possibly be used. In weeks where they see the therapist, they can record whether that person has mild or severe symptoms. And then, in a week like week N, where they don't see the therapist but they have severe symptoms, they could get a call to set up an appointment. Now I'm going to talk about our data collection. The data consists of Wi-Fi updates from connections to buildings at the University of Michigan. The locations are tagged with metadata including the GPS position and a functionality. The functionality is manually labeled and it includes labels like class, study, dorm, lab, and library. We label each location with one or two functionalities. I want to talk about some pros and cons of using Wi-Fi data because a lot of the prior work has used things like GPS or cell phone pings. This data is automatically linked to locations unlike GPS, which is nice. And also the data is likely available on most campuses, which means that something like this could be replicated because the data is going to be available for every student. A con is that we don't have data for when students are off campus, and this has implications for some of the downstream prediction tasks. For example, we don't really know if someone is at a bar until 1 a.m. or if they're studying at home. Students can also be connected to two access points at once, for example, from a tablet and from a phone. If they leave their tablet at home and bring their phone out, we don't actually know exactly where they are, and so we develop a pre-processing technique that we talk about in the paper. In addition to the location data, we collect personal data from the same students, and this is what we use for our downstream prediction tasks. For class year, we look at freshmen, sophomores, juniors, and seniors. For the school of enrollment, we look at the school that the student is enrolled in at the University of Michigan, and this can be engineering, LSA, and business. There are also some other schools, but we leave them out because the classes are very small. And then finally, we have the PHQ-8 depression score, and this is processed according to a clinically validated algorithm. For this, we do have the entire PHQ-8 survey embedded in the survey that we give to students. We also collect text that is related to locations, and this is what we use for our text-based representations. From Twitter, we collect tweets that are geotagged in Ann Arbor, which is where the University of Michigan is, and we use GPS coordinates to map the tweet to the nearest location. We say that a tweet has occurred at a building if it's within 50 meters. From this, we hope to capture how people express themselves in different locations. From Reddit, we collect data from the University of Michigan Reddit page. Specifically, we look at posts and comments that explicitly mention different locations, and we expand our search terms using OpenStreetMap, which has some different names for each of our locations. From this, we hope to capture how people informally describe locations. And finally, we collect data from the campus website. We start on this building search page, which lists sometimes a link directly to a building page, or it might list departments that are in the building. In this case, we would take each of the departments and do a Google search, and then take the first result on the University of Michigan domain. Then we would scrape the text from each of those websites. From this, we hope to capture how locations are more formally defined by the administration. Now I'm going to talk about our methods for building our embeddings. First, I'm going to talk about our trajectory-based method, or log2v. Traditionally, sentences have been used as input to Word2Vec. In our case, we look at sequences of locations that are ordered by the time at which they were visited. For each hour, we'll record exactly one location, which is the location where the person spent the longest time during that hour. This provides a precise meaning to adjacent locations in the sequence. For example, we might have a sequence like this, where there's a large gap between the visit to the chem lab and the math building. In this case, we wouldn't want those two to be adjacent because the person may have visited many different locations during that time, but they were off campus. So we insert this external token for the hours where we don't have information. Using the trajectory-based vectors, we hope to answer the question, what can we learn from how people physically interact with the world around them? Our second method is the text-based representations. We collected the 3 data sets that link locations to text, including from Twitter, from Reddit, and from the campus website. Then we create a weighted average of pre-trained glove embeddings for the words that are linked to those locations. We weight the embeddings using TF-IDF. Using this method, we hope to answer the question, what can we learn from what people say in and around physical spaces? Because we hypothesize that trajectories and text will provide different information about locations, we explore 2 different combination methods. The first uses a retrofitting approach based on a method for retrofitting word embeddings to semantic lexicons. In our case, we retrofit to a graph representing movement between locations. In our second approach, we simply concatenate the text-based and trajectory-based representations. Now I'm going to be talking about our experiments and our results. To recap, we have 6 different embedding methods. First, our trajectory-based method, log2v. Then 3 text-based methods using Reddit, Twitter, and the campus website. And then finally, 2 combined methods. The first here is the concatenation, and the second is using our retrofitting. We used Reddit for our combined approaches because we generally saw strong performance using Reddit embeddings for our downstream tasks. First, I'm going to be talking about 2 of our surface level tasks. Specifically, I'm going to start with functionality overlap. In this task, we look at what percentage of the nearest neighbors share at least one functionality. And for this, higher is better because it shows that the embedding space is encoding functionality. In this example, we have the Duderstadt library and its nearest neighbors, which actually don't share any functionalities with it. So in this case, the functionality overlap would be 0. For our results, we first look at an overall average, which is the average metric computed over all of the locations for each location. We see that this is around 20%. We find that this is exceeded by log2v, but all of the text-based representations actually do even better, as you see with Twitter, Reddit, and the campus website. By concatenating, we're able to get better results than we are from Reddit alone, while retrofitting leads to similar performance when compared to just Reddit data. For our physical distance task, we look at the average distance in kilometers to the nearest neighbors. In this case, lower is better because it means that the nearest neighbors are close in physical space as well as in the embedding space. In this example, all of the buildings are quite close by, within 0.2 kilometers. We see that our overall average here is 1.55 kilometers. The log to v yields the best performance on this task, while the text-based methods still outperform the baseline, as you'll see with Twitter, Reddit, and the campus website. By combining the Reddit text data with the trajectory information, we get better results than using Reddit data alone, as you'll see here, but we do not reach the performance of log to v. We find that the two methods, trajectory-based and text-based, yield opposite results on the two surface-level tasks. The combination method provides a good compromise with mid-range performance on each task. For our downstream tasks, we use an SVM. I invite you to look at the paper for details. We aggregate locations using a weighted average based on the time spent in each location to create an instance for each student, and then predict personal attributes. We use two baselines, a random baseline and a one-hot baseline, in which each location is represented by a one-hot vector, with those vectors aggregated to represent each student. The metric we report is macro F1, as some tasks have more than two classes and others, including depression, have a large data imbalance. For class year, we see the strongest performance using one-hot representations. We hypothesize that this is because those representations clearly represent, for instance, whether a student spends a lot of time in dorm buildings that primarily house freshmen. However, all of the embedding methods still allow us to significantly outperform the random baseline. For school prediction, we see strong performance using our Reddit text-based representation and our combination models. All of these methods outperform the random baseline. These two tasks are very clearly linked to location. Freshmen will spend a lot of time in dining halls, for instance, and the university actually has a separate campus that hosts mainly engineering classes. The next task that we look at is depression, for which the connection to location is not as strong. However, we are still able to exceed the random baseline. The Reddit and concatenation methods lead to the best results. We did not see too many students with depression in our study, and so we believe that if we had more data, we could learn more patterns that might be associated with depression. While results vary between our different tasks, we find that the concatenation method, which takes into account both location trajectories and text data, has strong overall performance. Such a model should be considered in future work on location embeddings because of its robustness on varied tasks. To conclude, I will readdress all of our research questions. First, do location embeddings encode meaningful semantic information? Using our surface level tasks, we found that yes, all of our embedding methods encode physical distance and functionality. Second, what types of data are most informative about locations? Using text data tended to inform us more about functionality, while using location trajectories tended to inform us more about physical distance. We see that this is a bit of a trade-off. On our downstream tasks, the results were text dependent, but we found that we did quite well with the combination method. And finally, can location embeddings aid us in downstream tasks? When predicting school and depression, we saw slightly stronger performance with location embeddings. For other tasks that require more surface level information, like, for example, students visiting a lot of dorms, the one-hot vectors ended up leading to better performance. Thank you.